Welcome to Yaka Digital Network. When we talk about electricity, we first need to understand voltage. Think of voltage as the electrical pressure pushing charges through a circuit. Looking at this massive body of water, Lake Victoria, imagine a giant tank perched above it. The physical water pressure that tank would provide is exactly how voltage behaves in a wire. Once that pressure pushes, we get current. Current is the actual flow of electrical charge. Look at this steady, relentless stream of boda-bodas navigating a busy Kampala street. That exact type of forward movement is your electrical current traveling through a conductor. But that flow rarely has a perfectly clear path. It encounters resistance, which is the opposition against the flow of current. See this thick, tangled undergrowth of the windy, impenetrable forest? Trying to push your way through that heavy brush to reach the gorilla is exactly what electrical resistance feels like for the current. To connect these variables, we use Ohm's law. This equation shows the golden rule. Voltage equals current multiplied by resistance. We can mathematically rearrange this. To find current from a 12-volt battery through a 4-ohm resistor, divide 12 by 4, giving 3 amperes. Grasping how pressure, flow, and opposition interact is the essential first step to reading and building any electrical circuit. Let's look at how we actually wire these components together, starting with a series circuit. This diagram shows components connected end-to-end in a single continuous loop, much like people walking single file on a narrow village path. Because there is only one route, every time we add a component, we add more opposition. Finding the total resistance here is as simple as summing them up, R1 plus R2 plus R3. Now, there is a common trap here. Many people think that as electricity pushes through each of these resistors, the current itself gets used up or weakens along the way. That is entirely incorrect. Current is the flow of charge, not a fuel. Notice these readings on the diagram. The exact same amount of current that leaves the battery is passing through every single point in this loop and returning to the source unchanged. While the circuit's total resistance increases with each new component on the path, the physical volume of charge flowing through it remains absolutely constant from start to finish. Things behave very differently in a parallel circuit. As you can see in this layout, the main wire splits into multiple separate branches. It is like having 3 different paths to reach the same well. If one path is blocked by a blown bulb, the others still work perfectly. Let's test this logic. If we have 2 10-ohm resistors placed in parallel like this, will the total resistance of the circuit be more than 10 ohms or less? Pause the video and think about your answer. The answer is less than 10 ohms. This can feel counterintuitive, but think of it like traffic. By adding another parallel branch, we are opening up an entirely new lane on a highway. Even though we added a resistor, we actually provided more total routes for the electricity to travel, which decreases the overall struggle. This unique trait makes parallel wiring the standard for household lighting and appliances. It allows multiple devices to draw power independently and efficiently without interrupting the whole system. Every circuit ultimately serves a purpose, and that purpose happens at the load. The load is the component that takes this flowing electrical energy and converts it into useful work, such as heat, motion, or light. Think of the load exactly like this plate of matoke and stew. You consume the food to convert its raw potential energy into the physical energy you need to go dig in the garden. We measure the rate of this energy conversion as power. Looking at this formula, power equals voltage multiplied by current. So a circuit with 10 volts of pressure and 2 amps of flow produces exactly 20 watts of power. Before you head into your O-level exams, get ready to take a screenshot of the next frame. This table breaks down everything we've covered. Notice how series circuits maintain a constant current but are stopped by a single failure, whereas parallel circuits divide the current, survive single-component breaks, and actually lower total resistance as they expand. For more step-by-step classes and comprehensive study materials, visit us at yaka.cc. By understanding how voltage pushes, how resistance fights back, and how paths dictate flow, you turn electricity from an unpredictable hazard into a precise, highly controllable tool for engineering.